Question 18 asks me to consider a left-tailed test with alpha equals 0.01 and find the appropriate rejection regions. Again, whenever we've looked at a question like this, I've referred you to slide 10 of the proportions PowerPoint. It literally tells you what to do for every possible region of rejection. There's only really 9 possibilities. There's 3 possibilities for alpha values, 0.01, 0.05, and 0.10. There's 3 possibilities for alternative hypotheses, less than, greater than, or not equal to. In this case, since it says it's a left-tailed test, it's a less than test. If we think about graphically what's happening, that means that there's going to be a region of rejection on the left-hand side, which has 0.01 area in it. Because it's only on the left-hand side and not on the right, when we look for a z is greater than, there's no rejection region on the z is greater than side. That's why we write in capital letters, N-O-N-E, the way that it tells us to in the instructions. When we look at the left-sided value, really the way that we get this value is by going into our table looking for 0.0100, but again, you don't have to go through all that if all you have is slide 10 in your notes, where it tells you for a one-tailed test at 0.01, the z value is negative 2.33. So again, hopefully you're just trying to match up column and row and directly from your notes put in what these rejection regions should be. Now that I have the rejection region, it gives me a test statistic to try, specifically negative 2.48. So this represents negative 2.33, the start of my rejection region. If I get something to the right of that, in this white area, I would fail to reject, or there would not be sufficient evidence to reject the null. If it lands in this dark shaded area, it's in the region of rejection, and there is sufficient evidence to reject the null. In this case, negative 2.48 is to the left of negative 2.33 in that region of rejection, so my conclusion is there is sufficient evidence to reject the null. Final question on the sample final and on the final is a full hypothesis test. In this case, it tells me that we had a random sample of n equals 1,400 observations from a binomial population. We had 674 successes. We want to show that the proportion differs from 0.5. Here, when it tells us the proportion differs from 0.5, the key is that it doesn't tell us it's greater than, doesn't tell us less than. Only thing we can do is use a not equal to test. So when I go to set my alternative hypothesis, it's that the proportion is not equal to 0.5. No matter what, my null is always equal to the same thing. Now that I have my null and alternative, it's time to calculate my test statistic. In order to do that, I first am going to need to find my p-hat. P-hat here is going to be based off of x, 674, over n, 1,400. When I put that into my calculator, 674 divided by 1,400 gives me an answer of 0.4814285714. I'm writing all these digits out basically because I'm trying to say that previously I told you just to cut it at 0.48, which is what I'd have you do on a paper test. But to make this match up with the answer that they're going to get in Cengage, I really don't want to round this at all. So you might be better off putting it directly into your z-score as parentheses 674 divided by 1,400 and then subtracting 0.5 from that. If you do it that way, we don't have to worry about the rounding being differently than their rounding. This all goes over the square root of the p under the null hypothesis, 0.5, times 1 minus that p, 0.5, over the given n, 1,400. Again, be very careful how all these parentheses go in to make sure that your calculator knows to do stuff in the right order. So I'm putting in parentheses 674 divided by 1,400 minus 0.5 divided by parentheses the root of parentheses 0.5 n parentheses new parentheses 1 minus 0.5 n parentheses divided by 1,400 and parentheses. As always, I'm trying to make it as clear as possible. All this stuff happening under the root is the crucial part of the problem. When I put this all in, I get a z-score of z equals negative 1.3897. I'm rounding to 2 decimals, so what I'm dropping is this 9, meaning I have to round up. That's how I get negative 1.39 as my test statistic. It now asks me to find a region of rejection to compare that to. Here I have alpha equals 0.05, and I know from above that it was a not equal to test. So I go to that third column for a two-tailed test. I go to the second row for alpha equals 0.05, and that tells me my regions of rejection are based off z being greater than 1.96 or z being less than negative 1.96. If these numbers look familiar, they should be. They're the numbers we use for confidence intervals. For any of the two-tailed tests, they're exactly the same as confidence intervals. So a not equal to test at 0.01 is going to be 2.575. A not equal to test at 0.05 like this is going to be 1.96. And a not equal to test at 0.10 is going to be 1.645. Regardless, now that we have this rejection region set up, we can graphically say that we have here at 1.96 the start of a rejection region, and here at negative 1.96 the start of a rejection region. If I try and place this negative 1.39 within my graph, it's here in the unshaded region. When it's in the unshaded region, that's when we fail to reject. The way that they phrase it in Cengage is they say there is not sufficient evidence to reject the null hypothesis, or the null is not rejected because there's not sufficient evidence to reject it.